On the shoulder of the constellation Orion sits a red star called Betelgeuse. For years, people have whispered about it as a kind of cosmic time bomb, wondering what would happen to our sky if one day it finally exploded. Imagine placing Betelgeuse where our sun is now. This red giant would swell so much that its outer layers would swallow the entire orbit of Mars. Inside, it's built like an onion of fading fuel shells of hydrogen, helium, and iron slowly running out, pushing the star closer to its inevitable fate, a brilliant supernova sometime in the distant future. On our way to understanding Betelgeuse, we'll step back and look at traces of other stellar explosions that once sprinkled iron-60 onto Earth, and see why only supernovae within a few dozen light years pose a real threat. Thanks to its distance of hundreds of light years, Betelgeuse sits safely beyond that danger zone, more like a promise of a spectacular harmless firework hanging in the night. What remains is a deeper mystery. Is Betelgeuse truly spinning fast because it once ate another star, or are we being fooled by a turbulent surface and the limits of our instruments? The journey to untangle those questions and to see what this red giant is really hiding begins now. On a clear winter night, if you look toward the familiar outline of Orion, your eyes are almost always drawn to a single point of soft, burning red. That is Betelgeuse resting on the hunter's left shoulder, a quiet ember hanging above our world. To the naked eye, it is simply one of the brightest stars in the sky, ranked around 10th in brightness, yet it has a presence that feels larger than its number. Astronomers classify Betelgeuse as a red supergiant, a star that began its life several times more massive than our Sun and has now swollen to an enormous size as it nears the end of its life. Its surface temperature is cooler than many of the blue-white stars around it, which is why it glows with that deep orange-red tint like metal heated and then beginning to cool. From Earth, Betelgeuse is roughly 600 to 700 light-years away close by on the scale of our galaxy, but comfortably distant for us. Tonight, the light reaching your eyes left this star centuries ago, crossing the dark between the stars, while entire human civilizations rose, struggled, and changed beneath it. Knowing where it lives in the sky is our first anchor, a quiet point to return to. If you could somehow place Betelgeuse where our Sun is now, the solar system would instantly feel too small for it. Its swollen atmosphere would stretch almost as far as the orbit of Mars, and in some estimates even beyond, turning the familiar clockwork of the inner planets into a furnace of thin glowing gas. A star that once was only a few times larger than the Sun has expanded until its radius is roughly 800 to 900 times greater, occupying a volume so vast the mind can barely hold it. Yet for all that size, Betelgeuse is surprisingly light in another sense. It is only around 10 times the mass of the Sun scattered through that enormous sphere. The result is a density so low that if you could somehow scoop up a handful of its outer layers and place them in a gigantic container, they would feel more like an ultra-thin fog than any solid substance. Gravity at its surface is gentle, almost hesitant, struggling to hold on to that drifting gas. In that contrast, immense size, delicate grip, Betelgeuse begins to feel less like a monster and more like an aging giant, expanded, loosened, and waiting for the next act in its long, slow, quietly unfolding, still unfinished story. Because Betelgeuse has spread its mass across such a vast volume, its surface gravity is far weaker than that of more compact stars. Near the edge of its swollen atmosphere, gravity pulls, but only softly, almost politely. Gas in those outer layers is only loosely bound free to rise cool and drift away into interstellar space. For a star in this late stage, holding itself together is no longer a simple task. Across that enormous surface, giant convection cells churn like slow luminous storms. Each one can be hundreds of millions of kilometers across, larger than the orbits of some planets in our own system. Hot plasma wells up from deeper layers, brightening patches of the star, then cools and sinks back down, setting up a restless boiling pattern that can change its apparent brightness over time. From our distance, we see only the combined glow, but high-resolution observations reveal a surface that is anything but calm. If you imagine standing on a distant world nearby, Betelgeuse would not look like a perfect smooth disk. It would resemble a heaving ocean of fire, mottled and uneven, breathing in slow motion. That uneven breathing is one of the keys to its mystery, shaping the light that finally reaches us here centuries after it first left home. In our galaxy, supernovae are rare on a human timescale, yet almost routine on a cosmic one. Astronomers estimate that in the Milky Way, perhaps 2 or 3 stars explode every century their deaths, briefly outshining the combined light of billions of quieter suns. Most of these events happen far from us, veiled behind dust, discovered only after the fact in lingering clouds of gas and exotic elements. For Earth, the key question is not whether stars explode, but how close they are when it happens. Energy from a supernova spreads out like ripples from a stone dropped into a pond, weakening as it travels. A detonation on the other side of the galaxy is a spectacle, not a threat. A detonation uncomfortably near could in theory disturb the chemistry of our atmosphere and the stability of life itself. So when we speak of risk, we're really talking about geography on a galactic scale, where we sit where the star sits, and how much of that invisible distance lies between our fragile blue world and someone else's final flare. Our own sun does not drift through the galaxy alone. It travels inside a vast, gentle cavity in the interstellar medium known as the local bubble, a region of thinner, hotter gas stretching for hundreds of light years in several directions. When astronomers map this bubble, they see something that looks almost like the hollow left behind by overlapping shockwaves, as if our part of space were carved out by ancient blasts. The leading idea is that this bubble was sculpted by multiple supernovae over the last 10 to 20 million years, each explosion sending shells of gas racing outward, clearing and heating the space between the stars. Over time, these shells merged and faded, leaving behind the low-density cavity the sun now quietly moves through. It is a strange thought our solar system, with all its delicate life and history, floats inside the long-cooled footprint of dead stars. Their violent endings happened long before humans existed, yet their echoes shape the environment we inhabit even now. The local bubble is a reminder that supernovae are not just distant fireworks. They are architects slowly rewriting the structure of space around us, deep in ancient seabed sediments and in slow-growing crusts on the ocean floor. Scientists have found something that does not belong to ordinary Earth geology traces of the radioactive isotopes, iron-60 and manganese-53. These atoms do not last forever, they decay over millions of years. Their presence in relatively young layers suggests that a few million years ago, Earth was dusted by material forged in the heart of a nearby supernova. It is as if a distant star exploded and a faint mist of its ashes eventually settled onto our world. Some researchers have gone further, wondering whether such events might have left not only chemical fingerprints, but biological ones. One speculative idea links a later influx of high-speed debris fragments, travelling at 10 to 40,000 kilometers per second, to climate disruptions and the decline of large animals like the woolly mammoth around 13,000 years ago. In this picture, supernova ejecta or associated impacts could have nudged Earth systems just enough to tip them into a new state. These connections are far from proven, and many scientists remain cautious. Yet the very fact that we can ask such questions hints at how intertwined we are with stellar death, how the fates of distant suns may on rare occasions brush the edges of our own story. When we step back from the details, a pattern begins to emerge. Supernovae can and do leave marks on Earth, faint layers of iron-60 in the seafloor, subtle changes in our local galactic environment, perhaps even gentle pushes to climate and ecosystems. They are not irrelevant to us, but they are also not constant nearby disasters waiting to strike. For a supernova to become truly dangerous, it must occur within a relatively small radius, in cosmic terms perhaps a few tens of light years. Most explosions happen far beyond that, their shockwaves diluted long before they reach our skies. Over the last 20 million years, life has endured several such distant events and continued to adapt, diversify and persist. So our provisional conclusion is simple and quietly reassuring: supernovae are powerful, but distance is a strong shield. From far away, their role is more sculptor than executioner. To understand what it means for a star like Betelgeuse to explode, we have to step into a realm where familiar forces are pushed to their limits. Inside any star, two great influences are constantly negotiating gravity, pulling inward, trying to crush everything toward the centre, and the pressure from nuclear fusion pushing outward, trying to hold the star up. For most of a star's life, these forces balance in a quiet, almost invisible truce. In a supernova, that balance fails catastrophically. Deep in the core, fusion can no longer provide enough pressure to resist gravity. The central regions collapse in a fraction of a second, densities soar beyond anything we can recreate on Earth, and the infalling material rebounds or is blown outward in an immense shock. In that short moment, the star releases more energy than our sun will emit over its entire lifetime. From far away, we see only a sudden brightening, a point of light swelling and fading. But behind that brief flare is a story of competing forces of stability lost and structure rearranged. Betelgeuse is one of the stars slowly approaching that threshold, still in balance for now, but already carrying the seeds of its final transformation. In one of the classic paths to a supernova, the star that explodes is not a swollen giant like Betelgeuse, but something much smaller and stranger, a white dwarf. A white dwarf is the exposed core of a once ordinary star, the embers left behind after it has shed its outer layers. It no longer shines by active fusion in its centre. Instead, it is held up by a quantum pressure from tightly packed electrons, a delicate counterweight to gravity known as electron degeneracy pressure. On its own, such a remnant can sit quietly for billions of years. But if it orbits close to a companion star, gravity can begin to draw material from that neighbour, feeding the white dwarf in a slow, steady stream. As it gains mass and creeps toward a critical threshold about 1.4 times the mass of the Sun, theory tells us that its internal support fails. In a moment, carbon in its core ignites almost everywhere at once. A runaway thermonuclear flame races through the star, unbinding it in a titanic flash. The white dwarf is not merely damaged, it is erased. From our vantage point, these Type Ia supernovae have a remarkable regularity in their peak brightness, turning them into standard candles that help us map the scale of the universe. Yet behind that useful predictability lies an eerie image, a quiet, stellar corpse slowly fattened by its partner, crossing an invisible line and vanishing in a single incandescent sigh. It is one possible ending for stars, a reminder that even seemingly stable arrangements can hide a built-in point of no return. For Betelgeuse, the path to a supernova is thought to follow a different script. This is the territory of Type II explosions, the fate reserved for massive stars that keep their outer layers, while their cores quietly change. Betelgeuse began life many times heavier than the Sun. Over millions of years, it has burned its way through hydrogen, then helium, then heavier fuels, each new stage pushing energy outward and holding gravity at bay. Inside, the structure now resembles an onion made of elements, shells of hydrogen and helium burning farther out and deeper layers where carbon, oxygen, neon and silicon have had their turn. At the very centre sits the most ominous layer of all, a growing core of iron. Iron is special in a stark way. Fusing it does not release energy, it consumes it. Once the core becomes dominated by iron, fusion can no longer pay the pressure bill that keeps the star puffed up. As the iron core gains mass and crosses a critical limit, theory predicts that its support will fail. In a heartbeat, it collapses under its own weight. Densities climb to nuclear levels, and the infalling material slams into an abruptly stiffening core. Shockwaves form, neutrinos flood outward, and the outer layers are blasted into space. What remains may be a neutron star, or if the star is massive enough, a black hole. This is the broad outline we place over Betelgeuse, an aging red supergiant in the final acts of its fuel cycle, not yet at the tipping point, but steadily walking toward a moment when gravity will finally win. When a massive star explodes, the raw numbers are almost impossible to grasp. In a few seconds, a core-collapsed supernova can emit more energy than the Sun will radiate over its entire 10 billion year lifetime. Shockwaves tear through the star's layers, temperatures spike to billions of degrees, and a flood of neutrinos streams outward, ghost-like and almost unstoppable. For a brief moment, one dying star can rival the brilliance of an entire galaxy. Yet energy, no matter how extreme at the source, must still obey simple geometry. As the blast expands, it spreads over a growing sphere of space, thinning as the radius increases. Double the distance and the energy per unit area falls to a quarter. Multiply the distance by 10 and it drops to 100th. What is lethal close in becomes merely impressive a little farther away, and at great distances it becomes only a bright point in the sky and a whisper in the background of space. This is why astronomers care so much about how far when they speak of danger. The same event that could strip atmospheres within a few tens of light years becomes harmless spectacle a few hundred light years out. Between us and any given supernova lies a vast cushion of emptiness, silently diluting even the fiercest outburst into something the night sky can carry without breaking. Even when a supernova is too far away to physically scorch a planet, its light and high-energy particles can still matter. The main concern for worlds with atmospheres like ours is not instant incineration but chemistry. Intense bursts of ultraviolet X-rays and gamma rays can break apart molecules high in the sky, especially those that form the ozone layer. Ozone is our thin, fragile shield against the sun's harsher ultraviolet light. Disturb it badly enough, and more UV reaches the surface for years, stressing ecosystems from plankton in the ocean to forests on land. Models suggest that to cause truly severe global damage to Earth's atmosphere, a core collapse supernova would probably need to occur within a few tens of light years. This rough threshold, often quoted around 20 to 25 light years, is what scientists sometimes call the kill zone. Not a sharp boundary, but a useful guide. Closer than that, and the combination of radiation and cosmic rays could push our protective layers beyond their ability to heal quickly. Beyond that distance, the impact drops rapidly. There might still be subtle changes, slight enhancements in cosmic rays, faint shifts written into rock and ice, but not the kind of catastrophic disruption that would remake the surface world. In this framework, space itself becomes a safety feature. Each additional light year adds another measure of dilution, another quiet buffer between living planets and the brief, fierce pulses of dying stars. Betelgeuse, for all its drama, sits comfortably outside this dangerous range. Current estimates place it roughly 600 to 700 light-years away, dozens of times farther than the approximate 25 light-year kill zone. Even if it were to explode in a spectacular Type II supernova tomorrow, by the time that burst of energy reached us, it would be spread across an enormous sphere of space. Here at our small point on that sphere, it would arrive as light to admire, not as a weapon to fear. Between us and that distant star, our own sun adds another layer of protection. The solar wind constantly blows outward, carving a bubble in the surrounding interstellar medium called the heliosphere. Within this vast invisible cocoon, many incoming charged particles are deflected or slowed their paths, twisted by magnetic fields long before they approach Earth. A strong enough event very close by could still leave a mark. But for something as far away as Betelgeuse, the combination of geometric dilution and this solar shield makes the practical risk vanishingly small. So when you picture Betelgeuse on Orion's shoulder, you can let it remain what it truly is to us: a distant lantern, a future firework in the sky. Its story touches our curiosity far more than it could ever touch our safety. When astronomers say that Betelgeuse is expected to explode soon, they are not speaking the same language as a human checking a calendar. In everyday life, soon might mean minutes, hours, perhaps a few years at most. On the astronomical timescale, it can comfortably stretch to tens of thousands, even hundreds of thousands of years, and still feel like the near future. For a star that has already burned for millions of years, a remaining lifetime of 100,000 years is a brief final act. Calculations based on Betelgeuse's mass luminosity and internal structure suggest that it is in the red supergiant phase close to its end. That much is widely agreed. But whether the core reaches collapse in 10,000 years, 50,000 or closer to 100,000 depends on details we cannot yet see, directly the exact size and state of the iron core, the mixing of layers, the efficiency of energy transport. Our instruments can infer, model and simulate, but they cannot yet peer straight into the heart of the star. So we are left with a kind of double meaning. In cosmic terms, Betelgeuse is a ticking clock in its final seconds. In human terms, its imminent explosion could occur long after every person alive today has turned to dust, long after our languages have shifted and our cities changed beyond recognition. The star is genuinely late in its life. Whether we as a species will be there to see its last flare is a separate question. One reason some papers and headlines have hinted that Betelgeuse might explode within mere decades comes from how we estimate its size and distance. Both of those quantities feed directly into models of its internal state. If Betelgeuse is larger and closer than traditionally thought, then for the same observed brightness, it must be intrinsically less luminous, burning its fuel more slowly. But if it is larger and more luminous, its core may be more advanced, sitting closer to the threshold of collapse. Small shifts in assumed radius can ripple into large changes in the calculated time left. Recent work using precise measurements of its motion and angular size has suggested that Betelgeuse might be closer and smaller than older estimates, but other analyses still allow for a somewhat larger star. In scenarios where the radius is on the high end, theoretical models can place Betelgeuse much deeper into its late evolutionary stages, with an iron core perhaps already close to its critical mass. Under those assumptions, the remaining lifetime might shrink dramatically from tens of thousands of years to something more like a few centuries or even decades. For a moment you can imagine that version of events. Within a human timescale, somewhere in the near future, Betelgeuse brightens to rival the moon, hanging like a second reddish lantern in the night for weeks or months, then slowly fading into a new remnant. Civilizations would write songs about it, build stories and myths in real time as the sky itself changed. But it is important to remember that this is only one branch of possibility resting on specific choices for radius and internal structure. The uncertainties are still wide and many models remain comfortably in the not in our lifetime regime. Despite all the attention Betelgeuse receives, our picture of its interior is still blurred. We measure its brightness, its colour, its apparent size on the sky, and its motion toward and away from us. From these surface clues we build models of what must be happening inside, like doctors inferring the state of a heart from pulses at the wrist. It is a powerful method but an indirect one. We cannot see the iron core directly or weigh exactly how close it is to the critical mass that would trigger collapse. We do not know every detail of how material mixes between layers or how magnetic fields thread the star. Different assumptions about these hidden pieces can lead to very different lifetimes, all still consistent with the data we have. In practice, this means we live with a fan of possibilities rather than a single countdown clock. Some branches put the explosion far beyond the human horizon, a few bring it closer. For now, the honest answer is a blend of knowledge and humility. We know Betelgeuse is late in its life, we know the kind of end it will face, but the precise timing remains one of the star's quiet secrets. Seen from Earth over many decades, Betelgeuse does not shine with a perfectly steady light. Its brightness rises and falls in slow, irregular waves, sometimes over a few hundred days, sometimes over a period of roughly 100 days or more. Astronomers track these changes carefully, building light curves that look almost like the breathing pattern of a sleeping giant. Inhale, exhale, glow a little stronger, fade a little more. Yet when they try to fit these patterns into a single simple cycle, the star resists. Different rhythms overlap and drift as if several songs were playing at once inside the same luminous body. The underlying cause is thought to lie in the star's vast, unstable envelope. Pulsations, convection cells, and possible changes in how energy moves through the outer layers all contribute to the glow we see. Models can reproduce parts of the behaviour, but not all of it at once, leaving room for multiple interpretations. For Betelgeuse, these brightness variations are not just cosmetic. They are one of the few direct signals we receive from its interior processes, a subtle Morse code written in light reminding us that the star's inner life is still in many ways an unsolved puzzle. In late 2019, something happened to Betelgeuse that caught even seasoned observers off guard. Over the course of a few months, the star dimmed dramatically, fading to about a third of its usual brightness. In the familiar pattern of Orion, the left shoulder that had always burned a steady ruddy orange suddenly looked weakened, as if the giant had taken a long uneasy breath and not quite exhaled. Astronomers compared measurements and checked for errors, but the numbers held. Betelgeuse really was fading before our eyes. For a star already known to be near the end of its life, this abrupt change lit up the imagination. Was this the first tremor before the core collapsed? Was the long-predicted supernova about to unfold in our own era, turning night into a soft red twilight for weeks on end? Papers, talks, and countless articles ask the same question in different tones, from cautious curiosity to excited speculation. For a while, the sky itself felt like a live experiment. Each clear night brought new measurements, each small shift in brightness, another clue. And yet beneath the excitement there was also a quiet awareness. Stars have many ways to surprise us, and not every surprise is the one we are secretly hoping to witness. Follow-up observations, especially from the Hubble Space Telescope, began to shift the story of the Great Dimming in a quieter direction. High-resolution images and spectra suggested that Betelgeuse itself might not have lost as much intrinsic brightness as we first feared. Instead, it seemed that a patch of its outer atmosphere had been expelled, cooled as it moved away and condensed into dust along our line of sight. Rather than the star going out, a curtain had been drawn in front of part of its face. In this picture, a large convective plume rose from deep within the star, carrying hot material outward. As that gas expanded, it cooled and allowed dust to form, creating a temporary asymmetric veil that blocked some of the light headed toward Earth. When the dust dispersed or shifted, Betelgeuse brightened again. Still, questions remain. How often does the star shed such clouds? How much mass does it lose in these episodes, and do they tell us anything about how close it is to core collapse? The Great Dimming may not have been a prelude to an imminent supernova, but it was a reminder that Betelgeuse is restless changing and still capable of surprising us. For more than a century, astronomers have quietly wondered whether Betelgeuse is truly alone. Its motions across the sky and small persistent irregularities in its behaviour have sometimes hinted at an unseen partner, tugging gently on the giant star as they orbit a shared centre of mass. In the early days, these suspicions were little more than patterns in noisy measurements, easy to dismiss as instrumental error or the star's own internal turbulence. But the question never fully went away. As data improved, hints of a long-period variation on the order of about 2,000 days began to emerge. That slow repeating signal did not fit neatly with known pulsation cycles or surface activity. It looked, at least to some eyes, like the subtle wobble of a massive star responding to a smaller companion's gravity. Was Betelgeuse the solitary red shoulder of Orion, in fact? Part of a quiet, dimly lit dance for two, as monitoring continued, that slow, multi-year rhythm around 270 days kept reappearing in the data. Two independent research teams working with different instruments and methods both found signs that Betelgeuse was not simply pulsating in and out like a single breathing lung. On top of the shorter, irregular brightness changes, there was a long, gentle swell and dip, as if the whole star were being nudged ever so slightly on a regular schedule. Alongside the light variations, careful measurements of Betelgeuse's position hinted at a tiny wobble against the background sky. Not a dramatic swing, but a subtle, repeated drift, hard to see and easy to miss without years of precise observations. When astronomers combined these clues, one explanation began to stand out. Betelgeuse might be moving in response to a companion star less massive and far fainter, orbiting at a distance comparable to the spacing between the Sun and Saturn. If that interpretation is right, the long-period cycle is not simply an internal heartbeat, but the footprint of an invisible partner, tracing slow circles in the dark. In the grand lantern of Orion's shoulder, there may be a second, quieter flame hidden in the glare. To move beyond hints and wobbles, astronomers turned to some of the sharpest eyes available on Earth. Using the Gemini North Telescope in Hawaii, equipped with high-resolution imaging techniques that can partially tame the blur of our atmosphere, they tried to peel back the glare of Betelgeuse and look for anything hiding close beside it. This is a difficult task. The main star is enormous and brilliant, the suspected companion far smaller and much fainter, lost in the glow. After painstaking processing, the team reported a tantalizing result. In the washed, speckled halo around Betelgeuse, they found a tiny persistent knot of light that seemed to sit at just the right distance and orientation to match the orbital hints from timing data. It was not a crisp photograph of a second star, nothing that would look impressive to a casual viewer. It was more like a smudge that stubbornly refused to vanish as the algorithms cleaned the image. On its own, such a feature could be noise, an artifact, or a coincidence. But together with the long-period variations and the subtle positional wobble, it strengthened the case for a hidden companion, a small star perhaps not much heavier than our Sun, circling an aging giant in slow, patient loops. If Betelgeuse truly has a companion, the discovery does more than satisfy curiosity. It changes how we read the star's behaviour as a kind of clock. For years, some of the long, slow variations in its brightness were candidates for a fundamental pulsation period, a heartbeat, that might tell us something about its internal structure and how close it is to the end. If those multi-year rhythms are instead shaped by an orbiting partner, then they no longer point so directly to the state of the core. The tick we were listening to may not be the ticking of a bomb, but the soft footfall of a smaller star moving in its path. That shift is quietly important. If the 2,000-day cycle is orbital rather than internal, then one line of argument for an imminent explosion weakens. The models that use that period as a constraint on Betelgeuse's size and density have to be revisited. In many of those revised scenarios, the timeline stretches, not contracts, pushing the probable supernova further into the future. The existence of Betelbuddy, if confirmed, would make Betelgeuse more complex, but also in some ways more reassuring for us. There is, however, a different kind of drama folded into this picture. A companion in a wide orbit today may still face a harsh fate tomorrow. When Betelgeuse finally does collapse and release its stored energy, the space within a few astronomical units will become a region of intense violence. Any small star orbiting so close would be bathed in radiation, and shock waves its outer layers stripped or heavily disturbed. So the Beetle Buddy hypothesis touches the countdown in two directions at once. It likely lengthens the time we have to wait, and it sketches a more intimate tragic ending for the system itself, not a single star dying in isolation, but a final act that sweeps through an entire hidden partnership. When astronomers turned the Atacama Large Millimeter Submillimeter Array ALMA toward Betelgeuse, they were not looking at visible light at all. They were listening to the star in radio wavelengths mapping the motion of gas in its extended atmosphere. By tuning to specific spectral lines and measuring tiny shifts in their frequency, they could use the Doppler effect to tell which parts of the star's surface were moving toward us and which were moving away. The maps that emerged were surprising. Instead of a chaotic patchwork, ALMA saw a broad gradient, one hemisphere slightly blue shifted, the opposite side slightly red shifted. The simplest reading of that pattern is rotation. If one limb is coming toward us and the other is receding, the star as a whole must be turning like a slow wheel of fire. From those shifts, researchers inferred a surface rotation speed of around 5 kilometers per second, implying that Betelgeuse might complete a turn in roughly 20 years. For a red supergiant that has ballooned to hundreds of times the Sun's radius, that is startlingly fast, seemingly at odds, with the expectation that such bloated stars should spin only sluggishly, having traded most of their youthful spin for swollen size. One way to reconcile such rapid rotation with Betelgeuse's swollen size is to imagine that it did not spin up alone. In the stellar cannibalism hypothesis, Betelgeuse once shared its system with a smaller companion in a much tighter orbit. As the red supergiant expanded, its outer layers swelled outward until they brushed against the companion's path. Friction and tidal forces would then have robbed the smaller star of orbital energy, causing it to spiral inward closer and closer to the giant's core. In the final stages of that inward plunge, the companion's material and orbital angular momentum would be dumped into Betelgeuse's envelope. The engulfed star would be shredded, its gas mixed into the larger star's outer layers, while its former orbital motion lived on as added spin. What had been a tidy binary becomes a single, rapidly rotating giant carrying within it the ghost of a lost partner. This scenario is more than a dramatic story. It fits a broader pattern. Models of massive star evolution show that many high-mass stars probably exchange mass merge or engulf companions during their lifetimes. If Betelgeuse's rotation really is as fast as ALMA suggests, a past act of cannibalism is one of the cleaner routes to get there. It would mean that even before its final explosion, Betelgeuse has already rewritten the architecture of its own system. There is, however, a very different way to read ALMA's map, one that does not require Betelgeuse to be spinning unnaturally fast or to have devoured a former companion. In this alternative, the apparent rotation signal is not a true spin at all, but an artifact of a messy boiling surface viewed with imperfect vision. Betelgeuse's outer layers are dominated by enormous convection cells, plumes of hot gas rising and cooler gas sinking on scales larger than the orbit of Earth. Those flows naturally create patches where material moves toward us and patches where it moves away. If you could see every patch clearly, the pattern would look mottled and uneven, with many small blue and red-shifted regions scattered across the disk. But ALMA, powerful as it is, cannot resolve all that fine structure. Its view is blurred, averaging over large areas. In simulations, when astronomers take a realistic turbulent surface and then smear it to ALMA's resolution, a broad gradient often appears, one side slightly more blue, the other more red, mimicking the clean signature of rotation, even when the underlying motions are far more chaotic. In these models, something like 90% of random convective patterns can masquerade as a smooth spin when seen in low detail. That sobering result suggests that Betelgeuse's supposed rapid rotation might be at least in part an illusion born from limited resolution and a restless, stormy atmosphere. The tension between these two pictures of Betelgeuse, the cannibal giant spinning on stolen momentum, and the turbulent star only pretending to rotate so fast, has become one of those quiet, productive disagreements that astronomy thrives on. On one side, the rotation interpretation offers a neat, physically motivated story that links Betelgeuse to a broader family of massive stars shaped by mergers and engulfed companions. On the other, the optical illusion view reminds us how easily complex surfaces can deceive us when seen through the soft focus of limited resolution. Both explanations are grounded in real physics. Both are supported by serious modelling. Neither has yet closed the case. What will tip the balance may be a new generation of observations, sharper, interferometric images that can resolve smaller surface features, longer-term monitoring to see whether the supposed rotation pattern remains stable, and better, simulations that couple 3D convection, radiative transfer, and realistic instrument effects. It is possible that the final answer will not be cleanly binary at all. Betelgeuse might rotate somewhat faster than expected, and still have its apparent spin exaggerated by giant convective plumes. The truth could be a layered compromise where cannibalism, turbulence, and instrumental blur all play a part. For us watching from a safe distance, there is a gentler lesson in this debate. Even with an iconic star that has been observed for centuries, our understanding still shifts when we find a new way to look. A smooth gradient can turn into a turbulent sea, a confident story into a branching tree of possibilities. Betelgeuse invites us to stay curious without pretending to be certain, to treat every map as provisional, and to accept that some of the universe's most luminous beacons are also among its most elusive mysteries. By now, Betelgeuse should feel a little less like a threat on the edge of the sky, and more like a distant character you've come to know. We have followed it from Orion's shoulder into its swollen interior, through layers of nuclear ash and drifting dust, past the hints of hidden companions and the puzzles written in its changing light. What began as a so-called cosmic time bomb has softened into something more nuanced, an old star in a complicated final act, far away, bright enough to fascinate but too distant to harm. One day, whether in thousands of years or far beyond any human story, Betelgeuse will finally give in to gravity and briefly outshine almost everything around it. When that happens, some eyes in some future night will look up and see a new beacon, perhaps large enough to cast shadows, perhaps bright enough to reset their myths. For them, it will be a live event. For us tonight, it is only an idea, a quiet possibility resting on the far side of deep time. Here and now, nothing has changed. Orion still rises and sets. Our sun still draws its protective bubble around the planets. Life on Earth continues under an ordinary sky, even as we let our thoughts wander out to a giant star nearly 700 light-years away. As you close your eyes, you can imagine that great red lantern still hanging there, breathing slowly, holding its secrets for another age. If sleep comes, let it come with the sense that the universe is vast, dynamic, and yet for this moment gently distant. Betelgeuse will keep its silent watch above, and you are safe below, carried through the night on a small blue world that has already outlived many explosions and will outlive many more. There is also a quieter way to leave Betelgeuse tonight, not as a puzzle to be solved, but as a rhythm to fall asleep to. You can picture its slow changes in brightness, as breaths spread over years, each inhale and exhale lasting longer than a human lifetime. The star brightens, it fades, it sheds a cloud of dust, it steadies again. Nothing in its behaviour moves on the scale of minutes or hours. Compared to its unhurried pulse, every worry and thought in your mind is a flicker, a brief spark on the surface of a much longer night. If you like, you can let that sense of scale wrap around you. The same physics that shapes Betelgeuse also holds the atoms in your bones together. The same universe that forges iron in collapsing cores has quietly supplied the iron in your blood. You're not outside this story, you're made from it. And yet despite that deep connection, the violence of distant stars reaches you now as nothing more than soft starlight and a calm idea before sleep. As you drift, Betelgeuse stays where it is far-read and patient. Its countdown, whatever numbers it holds, will go on without needing anything from you. Your only task is simple: to rest while the cosmos continues its slow, brilliant work overhead.